Okay, so welcome to this sixth lecture about concentration of measure. And today we shall finish the proof, we shall make the proof of the moment inequalities that we have stated last time. So I remind you that the quantities which are involved in those inequalities are quantities which look like quadratic variation in the theory of martingales, but which are a bit different. So we have the V plus quantities that we have seen appearing first in Efronstein's inequality. So this V plus is merely the expectation of the sum of the differences between Z and Z prime I square, positive part, knowing x1, xn, and you take the expectation knowing the variables x1, xn, and where the Z prime I are simply defined by the fact that at the number I coordinates, you substitute to xi the variable x prime I, and x prime I comes from a vector x prime, which is an independent copy of x. And Efronstein's inequality ensures that the variance of Z is less than this expectation of V plus. We have an alternative way to define some quantity which also looks like a quadratic variation. If you have at hand a family of x bracket I measurable variables, such that Z minus Zi is non-negative, then you can define the sum of the differences square between Z and Zi, and again, by Efronstein's inequality, you have that the variance of Z is less than the expectation of V. So in this case, you don't need, for Efronstein's inequality to hold, you don't need the fact that the differences are non-negative here, but nevertheless, we need this condition in order that the moment inequalities that we shall prove hold. So I remind you also the induction inequalities that we have got last time. So they are very simple to state. You have relationships between the Q order moments and the Q minus 1 order moments through this inequality here in the first case when you use V plus, and you have the analog in the V case, when you use V, you have about the same inequality. The only difference is that you have Q over 2 instead of Q minus 1, but apart from that, it's the same inequality. And now the purpose of the game is to derive the moment inequalities from this. And these moment inequalities will play the role of the exponential Efronstein's inequality that we have proved before, but at a different level, at a different scale. You are with power function instead of the exponential function. So it interpolates between the two, between the square and the exponential. So here is the statement of the inequalities that we have to prove here. As you see, it's a very, very simple statement. This is good news. And the proof is rather subtle, but not that difficult, as you will see in a moment. As a matter of fact, so we have the same result with V instead of V plus, exactly the same result. And as a matter of fact, as I say, we shall prove a slightly better result than this one. And since we shall use induction, it's not completely, when you use induction, If you have a stronger result to put in the machine, sometimes it's easier to use the induction argument. So this is exactly what happens here. You need a slightly better result in order to make the induction work. So the slightly better result is easy to state also, although the structure of the sequence tau q here may look strange, but as you will see, it's a natural structure which comes from the proof. And this sequence here is non-decreasing. So this means that, of course, it goes to tau when q goes to infinity. And if you have the same result as the result above with tau q instead of tau, of course, it implies the other result, which is slightly weaker. So this is exactly what we have to prove now. That is exactly the inequality above here, but with tau q instead of tau. This is what we shall prove. And of course, it will imply the final result. We shall make the same proof for the result involving V plus and the result involving V. You shall simply use a slightly worse constant. Instead of q minus 1 and q over 2, we shall use q, which is of course larger than q minus 1 and q over 2. So there is no ambiguity. And we shall use this slightly worse induction inequality to prove the result and have a common proof.
Monsieur, pourriez-vous montrer tau q? Il est un peu bloqué. OK. Oui, pourquoi ça tend vers tau?
Ça, c'est une question assez simple. Tu vois bien que quand q tend vers l'infini, tu as e puissance q sur 2 log de 1 moins 1 sur q, donc tu prends un équivalent et tu vas tomber sur racine de e divisé par racine de e moins 1. OK?
OK.
The monotonicity is not that obvious, but look at it and you will see that it is monotone. So we go to the proof. Proof of the moment inequality. Equalities, in fact. So we take some notations. We set nq equal z minus expectation positive part. And we start from an inequality that I shall denote by star as usual, and which says that nq to the power q is less than nq minus 1 to the power q plus q times nq to the power nq minus 2 v plus q over 2 or v q over 2. If we put q here, this inequality holds true both for v plus and for v. And we set CQ equal to tau q to the times v plus 1 sup q over 2. It looks strange here because in the statement q is larger than 2, but for the induction we need to start between 1 and 2, as I will explain you in a moment. So you take this here. And we want to prove that NQ is less than the square root of Q times CQ. I have just translated in terms of these new quantities, MQ and CQ, the results that we want to prove. And for the moment, what I say about tau Q is that tau Q is non-decreasing, and you will see that the choice of tau Q will become clear from the proof. So the way we want to do that is just use induction and prove the results for all Q between K and K plus 1, K being an integer, and we begin. I have to include and exclude somebody, but we don't care. And we begin, excuse me, just to make sure this should be excluded. Okay. And we begin with Q equal to 1 to start the induction. And how do we start the induction? We start the induction by using Effelstein. Just because, of course, the LQ norm, if Q is between 1 and 2, is less than the L2 norm, which is less than the square root of the L1 norm of V plus. And this is precisely the way we start the induction with, and this is the reason why here I have put 1 sup Q over 2. So what we shall use in the sequel is that both the families tau Q and CQ are non-increasing. This is what we shall use to pass from K to K plus 1. And more precisely, to pass from all the values of Q between K and K plus 1 and all the values of Q between K plus 1 and K plus 2. So we assume that the result holds true with Q minus 1. And we want to show that it's okay with Q. So it looks strange because, of course, induction works with integers and not with real numbers. But the way we do that is that we are doing an induction on integers, but we prove the results for all real numbers between the integer and the integer plus 1. This is the way we do that. Okay, so now I would like to renormalize the NQ by the CQs in order to get an easier result to prove. So this is the last notation that I shall introduce. I introduce XQ, which is NQ to the power Q over CQ to the power Q over 2 multiplied by Q to the power Q over 2. And so what we want to prove is that XQ is less than 1. And what we know is that xq minus 1 is less than 1. So now we rewrite the induction inequality with these new quantities xq. So remember what is the structure of star, which is there, okay? So you see that we have to substitute xq to mq, which is easy. And also we have to remember that the quantity which appears there, either v plus or v, is related to cq, okay? With tau q involved also. So we rewrite star, the inequality star, taking all this into account. That is, we substitute xq to mq, and we substitute cq and tau q to the v factor. So if we do that, we get something like that: q to the power q over 2, cq to the power q over 2 times xq. So this is exactly the nq to the power q factor term, excuse me. And we go on like that, less than xq minus 1 to the power q over q minus 1, multiplied by q minus 1 to the power q over 2, multiplied by c q minus 1 to the power q over 2. And about the last term, we have 1 over tau q multiplied by q times cq times xq times q to the power q over 2 times cq to the power q over 2, and xq to the power minus 2 over q times 1 over q cq. And this makes this factor here disappear.
C'est x ici, x c'est quoi? X c'est quoi? X, vous avez écrit. Non, non, vous avez seulement écrit en x puissance. X puissance. Ici, x puissance moins 2 sur q, c'est quoi? X.
J'ai compris. X cube.
X cube, okay.
Okay, now we divide by q to the power q over 2 times cq to the power q over 2. And we use the fact that cq minus 1 is less than cq. So this is important because this makes here appear a cq instead of cq minus 1. And you see that it's a good news, because after that, you have some homogeneity in the formula which appears. So at the end of the day, what you get is that xq is less than xq minus 1 to the power q over q minus 1 times 1 minus 1 over q to the power q over 2 plus 1 over tau q to the power xq times xq to the power 1 minus 2 over q. And now it's time to use our assumption. By our induction assumption, we know that xq minus 1 is less than 1. And so this means that xq is less than 1 minus 1 over q to the power q over 2 plus 1 over tau q times xq to the power 1 minus 2 over q. So this means that if we introduce the function fq of x, which is equal to 1 minus 1 over q to the power q over 2 plus 1 over tau q times x to the power 1 minus 2 over q minus x. This means that fq at point xq is non-negative. And now the function fq, it's easy to check that it is concave. The power which appears here is less than 1. So fq is concave. Fq at point 0 is non-negative. It's positive. And so the function fq has this shape. It's like that. And tau q is chosen in a way that fq is equal to 0 at point 1 here. So as you see in this picture, this the fact that fq at point xq is non-negative means that xq is somewhere here. So it's less than 1. And the proof is over. So the story is rather simple. When you build this proof, you don't know in advance, of course, what is the right choice of tau q to make, but you have a guess, which is that tau q has to be monotone. So you assume that it is monotone. At the end of the day, you make all this proof here, And you are lucky to discover that the choice that you have to make for tau q is indeed a monotone choice, and you won. So this achieves the proof of the moment inequality, this structural moment inequality. So as soon as you have done that, the idea now is to prove an analog of Lagrange inequality, but in the case where the variables at hand are not uniformly bounded. And it's doable through our moment inequality. So how to do that? So we consider, again, an empirical process, a centered empirical process, which means that the variables here are centered. And what we want to analyze is the moments of the difference between Z and its expectation. So it's a concentration at order Q in some sense. So at the second order, we already know that the variance is less than 2 times the expectation of W, where W is this quantity here, the soup of the sum of the square. And what we want to prove now is an explicit moment inequality, which involves what? Which involves the expectation of W, this is not a surprise, and which also involves a quantity which is the LQ norm of the soup of those variables. So this will play the role of a constant in the case where you look at Lagrange inequality. In the case of Lagrange inequality, this M was bounded by 1. Okay, but here you no longer use the fact that it is bounded by 1. It is what it is, and you relate the LQ moment for the difference between Z and its expectation and this quantity here, which is the LQ moment of the soup of the variables. So you get this. Take care of the fact that the way the second hand side of the inequality, the right hand side of the inequality, excuse me, depends on Q, differs in the first and the second term, because in the first term you have root of Q which appears, and in the second term you have Q which appears. And this is exactly the analog of what you see in Bernstein's inequality, where you have a sub-Gaussian term and a linear term which appears. It's the same here, because as you can easily check, if you happen to be in the statement, in the same condition as in the statement of Lagrange inequality, that is, if n is less than 1, you can use this inequality through Markov's inequality and try to optimize Markov's inequality with respect to Q. And you end up with an inequality which, apart from the absolute constants that you see appearing, has exactly the same structure as Bernstein's inequality. So this inequality really interpolates between the Lagrange inequality in the exponential case and Efronstein's inequality. This is the message. So the proof is very simple. So now we see the application to empirical processes. So we have already seen in the proof of Lagrange inequality that for empirical processes, the V plus quantity is less than small v plus capital W, where small v is the quantity that you like, that is the soup of the sum of the expectation of xit squared. This is a quantity that you expect, and W is not so nice, but it is what it is. It's a soup of the sum of the xit square. And why is it not so nice? Just because, of course, expectation of W is larger than the V that you would like to use. But anyway, it's like that. So you have to handle W is random, and you have to handle its fluctuations around its expectation. So you start with the first version of moment inequality, which involves V plus. I call it star again. And it tells us that Z minus its expectation, positive part, LQ norm, is less than the square root of Q multiplied by tau V plus the square root of Q tau multiplied by the LQ norm of the square root of W. It's just because the square root of the sum is less than the sum of the square roots, okay? And now we have to control this.
Monsieur, pourquoi V plus n'est pas apparu ici?
I have bounded V plus by the sum of these two terms.
Okay.
And as I've mentioned, the square root of a sum is less than the sum of the square roots.
Square root.
Okay. So I have bounded the square root of the LQ norm of the square root of V plus by these two terms here.
Okay.
The first one involves V, it's a constant, and the second one is random, it involves the square root of W.
Okay.
So now we have to handle the square root of W. And of course, the idea is to use the second version now. So let's do it naively and then correct what we have done. So let's do it naively. If we introduce Wi, which is the soup of the sum of the xjt square, And if we remember that M is the soup of all the variables, then if we do as usual, that is, we write we introduce T star such that W is equal to the sum of the xjt star square. So it's a point where the soup of the sum of the xjt square is achieved. If we do that, then the difference between W and Wi square is less than xit star. Take care, it's square to the square, so it's to the power 4. And it's less than m multiplied by xit square. So this means that since W...
Monsieur, pourquoi il y a M carré? Parce que M, peut-être il y a un M carré.
C'est M carré. It's M square. You're right. So since W is indeed the sum of the xit square, you end up with the fact that the sum of the W minus Wi square is less than m square times W. So it seems at first glance that it is a never-ending story because you make this W appear again. So what to do with that? So the trick is look at the square root. Instead of W, look at square root of W. Because when you look at the square root of W, then you have the sum of the square root of W minus square root of Wi square, which is of course equal to the sum of the W minus Wi square over the sum of the square roots of the Wi and the W square. And the denominator here is always larger than W. So that at the end of the day, the sum of the squares here is less than m squared W over W, that is m squared. So this is good news because now if we apply the second version of the inequality of the moment inequality to square root of W, what you get is that the square root of W minus the expectation of the square root of W, positive part, LQ norm, is less than the square root of tau Q times the LQ moment of M. And you have no longer W appear here. So now the proof is almost done. It remains to notice that the expectation of W is less than the square root of the expectation of W. And to combine the above inequality with star. So remember that star, what does it say? It says that you are less than that, which is a gentle term, and this term here, which was involving the LQ norm of square root of W, which is precisely what we have controlled now. So it amounts now to multiply by square root of Q tau in order to conclude. So this is what we do. So if we combine with star, what we get is that the expectation, the difference between Z and its expectation, positive part, the LQ norm, is less than square root of Q tau V plus the square root of Q tau expectation of W and plus the last term, which is Q tau times the LQ norm of M. And of course, this guy here is less than 2 times the square root of Q tau expectation of W. So you have the two terms which were announced in the statement of the inequality, that is this one and that one. Okay? And the proof is over. So you see there's two terms appear, this one and this one. Okay, it's a good time to make a coffee break, because after that we shall pass to another topic, which is the topic of the transportation method. So we stop for 5-minute break and come back after that. Let us come back to this lecture. And now we open we are opening the last chapter of this course. And this chapter will be devoted to the transportation method. So as you will see, you shall use entropy again with a different flavor and different types of arguments than before. So what is optimal transportation? It's of course a topic which is very important and it's important by itself in some sense. That is, it's important for many type of applications which are not related to concentration, but as you will see, it's also important for concentration. There is a link between transportation and concentration. So what is the Monge formulation of the problem? The Monge formulation of the transportation problem is the following. You have two probability distributions, P and Q. You have a cost function, which is denoted by W, and you want to go from P to Q, to push P on Q with a cost which is as less as possible. So this means that you want to minimize this integral here. And the map which appears here, the map T, has to be such that the distribution of this map under P is equal to Q. So this is what people call pushing P on Q. So a minimizer does not necessarily exist, but if it exists, this minimizer is called an optimal transportation map or plan, people say.
Monsieur, je ne peux pas comprendre la phrase. The probability distribution of T under P is equal to Q. Je ne sais pas, ça veut dire quoi?
You have this map T, which goes from X to X. Okay, it's the same space. P goes, T goes from X to X. Usually you have a space here which is called omega, and here you have another space. Okay, but here it's the same. So you have here a probability distribution which is underlying, which is P, and you want that the distribution here of T to be Q if the distribution here is P. You know what is the probability distribution of a random variable?
Oui.
It's the same concept. What is exotic here is that you have the same space here and here. Usually here you have omega and here you have Rn, okay?
Okay.
But here you have the same space, that's all. Okay, so this is the Monge formulation. So the Monge formulation has a default, which is that it's not necessarily, such a map does not necessarily exist, but nevertheless you want to relate P and Q. So there is another formulation of the problem, which is the modern formulation, and this is the one that we shall use. And this formulation is due to Kantorowicz. It's an extension of the preceding framework, and it's formulated in terms of coupling. That is, you want to build a joint distribution such that the first marginal is equal to Q, the second marginal is equal. The first marginal is equal to P, excuse me, the second marginal is equal to Q, and you want this to build this coupling distribution on the product space X cross X. And again, you want to minimize the cost, which depends, of course, of this coupling. The coupling is denoted by bold P here. Okay, so now the issue is to build an optimal coupling, that is a coupling which makes this cost as less as possible. So this is a generalization of the preceding formulation, because of course, if it happens that you have a transportation map, you have a coupling. The coupling is just the distribution of x tx. If you have a coupling, if you have a map, transportation map, if T transportation map exists, it implies that there is a coupling. But the converse is not necessarily true. So this, to establish the link between transportation and concentration, the engine that we shall use is the transportation lemma that we have already seen together. This was a consequence of the duality formula for entropy and its converse. So what we have seen is that it's possible to encode the sub-Gaussian property by the following here, which has something to do with transportation, as we shall see in a moment. So to see that it has something to do with transportation, let's look at the very basic, at a very basic level, what can be the link between transportation and concentration. So at this basic level, just look at Lifshitz functions. So you take a Lifshitz function with respect to some matrix D, and you look at some coupling. And the coupling between P and Q will allow you to write the difference between these two expectations.
Je vais vous montrer de dernière transparent parce que je voudrais voir un exemple. Merci beaucoup.
Okay, so what is important here is that as soon as you have a coupling between P and Q, you can write the difference between these two expectations as the expectation of the difference. Okay, here implicitly when I'm writing this, it means that the couple of variables has distribution as joint distributions p-bold, which is a coupling. Okay? So since the marginals of p-bold are respectively p and q, when you look at this, the expectation of the difference, since you are on the same space, you can write that it is the difference of the expectations. And individually, when you look at the expectation under p-bold of f of x, that it is indeed equal to the expectation of the function under p, just because the first marginal of p-bold is p. So if the function is Lifshitz, you can bound now the difference between f at point y and f at point x by the distance between x and y. And if you are able to relate the transportation cost, where the cost function is the distance, to the relative entropy between Q and P, then the transportation lemma allows to conclude that the function minus its expectation is sub-Gaussian with a constant which is merely L square, which comes from this, times C, where C just comes from the transportation inequality, which is there. Okay. So here you see the connection is very simple. You have, in the case where the function is Lipschitz, you have a natural cost function, which is the distance. And if you are able to relate the transportation cost with this cost function to relative entropy, then the transportation lemma tells you readily that you have a concentration. So this scheme here, we shall see that it works perfectly well in the Gaussian case. In the Gaussian case, we shall see that it's possible to prove the transportation inequality of this form here. And this transportation inequality itself will imply concentration just by using this scheme. Okay, so here the message is that the engine to get concentration, instead of being Herbst argument as in the entropy method that we have seen, or modification of Herbst argument, here we have another engine which is also based on the duality formula, and which is this engine here, which is this transportation lemma. Okay? So to see in details how it works, the best is to reproduce a proof based on transportation arguments of Mach-Dyer-Mitz inequality. This is what we are doing right now. So to produce this proof of Mach-Dyer-Mitz inequality, the essence of the proof is to consider a special cost, which is the most elementary cost, that is the 0,1 cost. You pay 1 if x is different from y. You pay 0 if x is equal to y. So if we look at this transportation cost, first we have that it's possible to completely determine what is the transportation cost related to this cost. Because when you look at the transportation cost, which is there, this transportation cost is exactly equal to the total variation distance between P and Q. So let's see that. First of all, we have to prove that when you take a coupling, the quantity which is involved, I've come back to the preceding slide, the quantity which is there, which is a probability that x is different from y, we want to show that this quantity is always larger than the total variation distance for all coupling. And after that, we shall have to build an optimal coupling and show that it achieves the total variation distance. So let's see that again. So we take some coupling and we write the difference between the probabilities of two events A here as the absolute value of the expectation of the difference between the indicator functions. Okay, I just use the fact that here the coupling has first marginal P and second marginal Q. After that, I use the fact that the absolute value of the difference between expectation is less than the expectation of the absolute value. Okay. And now I notice that the difference between these indicator functions in absolute value is always less than the indicator function of the event x is different from y. Okay? And so this shows that taking the expectation, the difference between P of A and Q of A in absolute value is less than the probability that x is different from y. And this is true whatever the coupling. So this means that the total variation distance is always less than the transportation cost. And now we have to build an optimal coupling. Since we have stated that it was a minimum, you have to build explicitly the optimal coupling. So this optimal coupling, which will achieve the total variation distance, will be constructed as a mixture. So first of all, we have to deal with the trivial case. In the trivial case, P is equal, the total variation distance is equal to 0, P is equal to Q, and we have nothing to do. So if we set A to be equal to the total variation distance between P and Q, we exclude the fact that A is equal to 0, otherwise it's trivial. And if A is positive, we construct P as a mixture, as I was saying. And to define this mixture, I need to take some notations. When I have two probability in my pocket, I can always assume that they are absolutely continuous with respect to some dominating measure. The dominating measure that you can produce here is just the sum between the two probabilities, P and Q over 2. So we have a dominating probability measure here. And you consider the densities of P and Q with respect to this dominating measure. And now the total variation distance, once you have a dominating measure, you can write it as an L1 distance or as half the L1 distance, excuse me, or as the integral of P minus Q positive part, or also as 1 minus the integral of P infimum of Q. And here, of course, the integral are taken under mu. Okay?
Monsieur?
Oui.
Qu'est-ce que mu et P, c'est-à-dire P et Q est dominé par mu, c'est ça? P et Q est dominé par Q, c'est ça?
P et Q sont toutes les deux dominées par mu qui est leur demi-somme. Quand tu prends mu, la demi-somme, elle domine à la fois P et Q. Donc tu as une densité.
Mais pourquoi la densité de P et Q existe? C'est-à-dire, lorsque P...
Ça s'appelle le théorème de Radon-Nicodim. Le théorème de Radon-Nicodim t'assure que quand tu prends une mesure qui domine deux probabilités comme ça, une mesure qui est cible infinie, ici elle est cible infinie, hein, c'est une probabilité, eh bien il existe toujours une densité. C'est le théorème de Radon-Nicodim.
Non, peut-être c'est une inverse, c'est-à-dire lorsque P est dominé par Q, c'est T mu sur TP.
Non, ce n'est pas ce que je dis. Ici, tu prends la demi-somme des probabilités, elle domine toujours les probabilités. Quand tu prends la demi-somme, P is always absolutely continuous with respect to mu, because when you have mu of A which is equal to 0.
Oui, je sais ça, oui, je sais ça.
Alors, quelle est ta question? Parce que là, il y a plus de questions.
Après un théorème, c'est T mu sur TP, n'est-ce pas? Il existe un T
Non,
mu,
c'est TP sur des mu.
TP sur T mu. Ah, je dois regarder. Je dois regarder.
C'est TP sur des mu.
OK.
Okay. So as I was saying, in this case, when you have densities, you can express the total variation distance as half of the L1 distance between these densities, or like that, the integral of P minus Q positive part, or as 1 minus integral of P infimum with Q. And now we defined our coupling as a mixture. It's a mixture between P1 and P2. So what is P1? What is P2? P1 is a product measure. It's a product probability measure. It's a product between the probability measure, which has density 1 over A, P minus Q positive part. So remember that the integral of P minus Q positive part is equal to A. So this makes this function a density. And you take the product of this probability measure with the other one, which is the reverse in some sense, that is, excuse me, there is a mistake here. It's not. Cannot be like that. It's not 1 over Q, it's, excuse me. Here it's Q minus, it's 1 over A also, so it's the same. So it's the other one, that is Q minus P, positive part, and 1 over A, it's still 1 over A. It's not Q. Okay. And the other one, P2, is concentrated on the diagonal, and it's concentrated on the diagonal with density 1 over 1 minus A times P infimum with Q. So remember that the integral of P infimum with Q is equal to 1 minus A. So this is also a density. So if you do that, then you actually get a coupling between P and Q, because when you look at the first marginal, its density is A over A times P minus Q positive part, plus 1 minus A over 1 minus A P infimum with Q. So it's the sum between P minus Q positive part and P infimum with Q. So this is equal to P. So this is for the first marginal. And the second marginal, you do the same calculation.
Attendez, la dernière transparence, s'il vous plaît.
When you compute the density of the first marginal, since you have a mixture here, you have A over A positive part of the difference between P and Q, which comes from this. And for the other part of the mixture here, for the second term of the mixture, you get 1 minus A over 1 minus A, P infimum with Q. And you simply use the fact that P minus Q positive part plus P infimum with Q is equal to P. So the first marginal of bold P is equal to P. And you do the same with the second marginal. So this means that you have a coupling, that is the first marginal of bold P is P, and the second marginal of bold P is Q. And now, when you look at the probability, the bold P probability that X is different from Y, it is of course equal to A times P1 of X different from Y. So it is equal to A. So this means that P is optimal. Okay? So this finishes the proof of the fact that we can compute the transportation cost for the 0,1 cost. You can compute it, and it is equal to the total variation distance. This is the first step. So now let us revisit the proof of Mark-Dyer-Means inequality with transportation arguments. So as you have seen, the first step was to compute the transportation cost when the cost is the 0,1 cost. The second step now is to bound the transportation cost by a quantity which involves the relative entropy.
Monsieur, pourquoi P1 à X n'est pas Y égale 1? Pourquoi P1 X n'est
So you can come to the proof.
Oui. Oui.
Here?
Oui. Pourquoi P1 X n'est pas Y égale 1?
P1 of X different from Y is equal to 1, yes? It is.
Pourquoi?
Look at P1. P1 is the tensor product of there's two densities here.
Oui.
What does it mean, tensor products? It means that when you look at the variable, if you take the couple xy, under P1, the variables are independent.
XY?
X and Y are independent, okay?
Oui.
So in this case, the probability that they are different is equal to 1.
Oh.
Think about it, okay?
Okay.
You have to convince yourself, you have to convince of that by yourself. Okay, so let us come back to the transportation approach. So we have computed the transportation cost, which is merely the total variation distance in this case of the 0,1 cost. And on the other hand, we have at hand Pinsker inequality, which says that, so we have Pinsker inequality here, which ensures that the total variation distance is less than the square root of the relative entropy between Q and P over 2. Remember that this Pinsker inequality, you have proved it as an exercise after having proved the transportation lemma. And it's a consequence of the 1 implies 2 part of the transportation lemma. Okay? So if we combine these two facts, first, the computation of the transportation cost is doable and it's equal to the total variation distance, and you combine this with Pinsker's inequality, then this leads to this inequality here, which is our first coupling inequality. That is an inequality which relates a transportation cost and relative entropy. Okay? Now for the next step, we have to pass from dimension 1 to dimension n. So remember that to pass from dimension 1 to dimension n, in the entropy method, the tool that we had in our pocket was the subadditive inequality. But here we need another idea. So we need an idea. And what is this idea? It is a nice idea introduced by Katalin Martel, and which consists of using the chain rule for relative entropy in order to build a coupling in dimension n, starting from a coupling in dimension 1. This chain rule, I shall come back to it in a moment, but intuitively, this is a formula which generalizes the well-known fact that if the probability Q happens to be a product probability measure, then the relative entropy between Q and Pn, which is indeed a probability measure, a product measure, excuse me, then this relative entropy is simply the sum along the coordinates of the relative entropies between the marginal distributions of Q and Pn. This is a well-known fact. So if Q itself was a product measure, the coupling would be very easy to build. It would simply be a coupling between the marginals. We would couple the marginals in an optimal way, and everything would be okay. Here, it's a bit different. It's a bit more complicated, but you have the chain rule, which will save you, because the chain rule will also have an additive structure. It will involve conditional entropies, but with an additive structure that will save you and will allow you to pass from dimension 1 to dimension n. So I now try to give you an idea of what is exactly the chain rule for relative entropy. We do it for dimension 2. In dimension 2, let us explain what is the chain rule. So you take P to be a product measure, a product probability measure in dimension 2, and you take Q, which is absolutely continuous with respect to P. So you take a pair of random variables, x, y, which has joint distribution Q, and you denote by G the joint density of the pair xy with respect to P. Now, if you denote by Gy the marginal density of y with respect to nu, you may define the conditional density of x given y with respect to nu as the ratio between the joint density and the marginal density. This is something that you have seen already, of course. And now the issue is to compute the relative entropy between Q and P, making appear marginal densities and conditional densities. So if we expand this integral here by using the fact that the joint density is equal to the conditional density multiplied by the marginal density, you expand the formula, you use the fact that the probability P is a product probability measure, and you use, of course, Fubini, and you have these two terms here. The first one is the one where in the log I have, of course, use the fact that the log of the product is the sum of the logs. And here I have kept the conditional density, and here I have kept the marginal density. And now the chain rule appears here. The first integral is a mixture under the marginal distribution of conditional relative entropies. And the second term is merely the relative entropy of the marginal distributions of Q and P respectively. Okay, so here you have this nice formula which has an additive structure. And of course, if it happens that the Q distribution is itself a product measure, this second term here would reduce to the relative entropy between the first marginals of the Q and the P distributions. But this formula generalizes on this fact. So we have something which is more general. So now, what does Martin's first coupling inequality says?
Oui. QY, c'est quoi? QY.
Pardon? QY, c'est la. It's a.
Vous pourrez remontrer la formule, oui.
Here, QY is merely the marginal distribution of the pair XY. It's the second marginal of the distribution capital Q. Capital Q is a two-dimensional distribution. Okay, it's a distribution of the product space, and the second variable has distribution Q Y.
Oui. Petit QY, petit QY dans
Oui.
le
QY, c'est la loi marginale de Y.
Ok, ça égale GY nu,
c'est
ça.
Ça pour densité GY.
Oui.
Par rapport à mu. Par rapport à nu.
Oui, ok, nu. Ok, c'est bon.
So what does Martin's first coupling inequality, because as you will see, there is a second one, but the first one tells you that the sum, you can build a coupling between Q and Pn in a way that the sum of the probability square that xy is different from yy is under control by the relative entropy between Q and Pn over 2. So this is a formula which has an additive structure and which is a generalization of Pinsker's inequality in dimension 1. So as I have already mentioned, you should not be surprised by this additive structure, because if the probability Q itself would happen to be a product measure, then the computation of the relative entropy between Q and Pn would merely be the sum of the relative entropies between the marginals. And in this case, of course, the optimal coupling would be very easy to build. It would simply be built by sticking the marginals together in an optimal way, and then use Pinsker's inequality to conclude. Okay, so now for the moment, I postpone the proof of Martin's coupling inequality, but I would just want to show you how Martin's inequality implies readily McDermott's inequality. Why does it imply McDermott's inequality? So it's very, very simple and very elegant, as you will see. So let's take the bounded differences condition that we have seen several times right now. So assume that the function f satisfies to the bounded differences condition, and take some probability q, which is absolutely continuous with respect to Pn. And to use the transportation lemma, we need to upper bound the difference between the expectation of f under q and the expectation of f under Pn. The fact that you have built a coupling allows to compute the difference of those expectations as the expectation of a difference, just because you have this coupling. And now you use the bounded differences conditions in the one hand to say that the expectation of this difference is always less than the sum of the CI expectation of the indicator functions, but expectation of the indicator function is just the probability that xi is different from yi. And then you use Cauchy-Schwarz to upper bound this by the square root of the sum of CI square and the square root of the sum of the P square xi is different from yi. And of course, now to bound this quantity, this is the very point and the very moment where I shall use the optimal coupling. If I use the optimal coupling given by Martin's coupling inequality, I shall be able to bound this sum of squares here by the relative entropy over 2 under the square root. So this is what I get. I use Martin's coupling and get a control, which is the product between the square root of the sum of the C squares and the square root of the relative entropy. So if I introduce V to be the sum of the CI square over 4, I readily get the shape that I like, that is the square root of 2V times relative entropy, which encodes the subgaussianity of f minus its expectation with a variance factor, which is V. And this is done through the transportation lemma. So you see that given the coupling inequality by Katalin Martin, we have proved Magdalén's inequality just using the transportation lemma. So you see that somewhere Hoeffding's lemma is always and also at the root of Magdalén's inequality, since Hoeffding's lemma through the transportation lemma and the 1 implies 2 statement has been the root to prove Pinsker's inequality, and Pinsker's inequality itself, through the induction principle brought by Katalin Martin, gives the Magdalena inequality through the transportation lemma again, but in the reverse sense. Okay?
Sir, can you hear me?
Yes.
Doesn't the transportation lemma say that for all Q, and here you take a Q which achieves the minimum, right? So I don't see how 2 implies 1.
Oh, sorry, I come back to the transportation lemma.
Thanks.
Where is it? it's there. So in this transportation lemma, you have two statements. The first statement is that the moment generating function has a sub-Gaussian control here, okay? And the second statement is that when you compute the difference between the expectation of z under q and the expectation of z under p, it is under control by the square root of 2v times the relative entropy, and this has to be true for all q, which is absolutely continuous with respect to p. So the optimization that we have done is not performed through q, it's performed through the coupling between p and q. Was it your question?
I'm not sure. I think we showed that this inequality was true for some q, which achieves the minimum.
No,
and to
no,
use,
no, no. This is okay. You mixed up two things.
Okay. For some p, bold p.
Yes.
Okay.
You are mixing up q and bold p.
Okay.
So q here is, sorry. Let's come back here. Okay. So q is whatever you like. It's any q, which is absolutely continuous with respect to p. And
okay.
what we have computed is a bold p here, which is the best choice for coupling q and p. So of course it depends on q, but for any q that you give me, I can construct a bold p.
Okay, thank you.
Okay, so it's still, at the end of the day, it's true for any q.
Thanks.
So now it remains to prove it remains to prove Martin's coupling inequality, and this is what we are now doing. It's not, excuse me. Martin's coupling inequality. So we proceed by induction.
Vous montrer encore une fois un petit peu Martin's coupling inequality. Merci. OK, merci.
It's there.
Oui, OK.
Okay, so by essence, what we have to do is to build a coupling.
Oui.
And the way we shall do that is, as announced, by using the chain rule. Okay, we shall use a chain rule. The chain rule will be our guide to build the coupling. So let's do it. It's not that complicated, but the notations are sometimes a bit difficult to fix. Okay, so we proceed by induction. So for n equal to 1, this is merely Pinker's inequality. Combined with the transportation cost computation with the 0,1 loss, 0,1 cost. Okay? So dimension 1 is easy. And now we assume that the result holds true, whatever Q, P minus 1, Q being a probability distribution on the product space whatever Q on the product space x to the power n minus 1. And we want to prove the result in dimension n. So what we do is to use conditioning with respect to number n coordinate. So we write Q as its density J times Pn on the one hand. Pn, remember, it's mu1 product mu2 product mu-n. And we take Jn to be the nth marginal density of Q with respect to mu-n. And so we have the marginal distribution of Q, which is Jn times mu-n. Then we introduce the conditional density. J of x given t, which is merely J of x and t over Jn over t of t. And this is for all x in x to the power n minus 1 and all t in calligraphic x. And at the end of the day, we have the conditional distribution which is the probability distribution, which has density, the conditional density, with respect to Pn minus 1. So we have fixed all the notations. And now we use the chain rule. We use the chain rule in dimension 2 because here we are looking at xn as xn minus 1 product with x. Okay, so we have a two-dimensional situation. And we use the chain rule in this two-dimensional situation and rewrite the relative entropy of Q with respect to Pn as the integral of the relative entropy between the conditional distribution and Pn minus 1. And it's a mixture under the marginal number n of Q plus the relative entropy between the marginals number n of Q and Pn. So this is the chain rule that we use here. And now you see that the chain rule itself, due to its structure, is leading us to what is the right construction to make as a coupling. Because you see that you have this term which appears, and this term just forces us to couple in an optimal way the marginals of Q and the n marginal of Q and Pn. This is what we want to do. And this also forces us to couple in an optimal way the conditional distributions here. But now, as you know, in dimension 2, to define a product, a joint distribution, you just need to produce what? To produce a marginal and a family of conditional distributions. So now you know how to build your coupling. You are building your coupling by coupling in an optimal way the number n marginals and produce a family of optimal couplings for the conditional distributions. So this is what we are doing. So we use the induction assumption to ensure the existence of a coupling bold P that I denote by bold P given T. It's a notation. And it's a coupling between Q given T that has been defined before and Pn minus 1 such that the sum between 1 and n minus 1 of the P bold square xy different from yi given T is less than the relative entropy between Q given T and Pn minus 1 over 2. And we use the one-dimensional result to build a coupling that I denote by P bold sub n between Q sub n and mu sub n such that the P bold sub n probability square that xn is different from yn is less than the relative entropy between Q sub n and mu sub n over 2. So now it remains to stick all these conditional and marginal couplings together. And this is quite easy to do. We merely define bold P on the space x to the power n cross x to the power n that we see as the product space x to the power minus 1 cross x to the power n minus 1 cross x cross x. This is the space where we have defined our conditional couplings. This is the space where we have defined our marginal couplings. And now we use simply the fact that, there is only one way to stick marginal and conditional distributions. So we define P just by saying that the marginal number n is equal to Pn, to P bold n, and the family of conditional distributions given the number n coordinate is the family P bold given T. If we do that, this by construction, P bold is a coupling between Q and Pn. Everything has been done to produce that because you have a construction which is consistent with the conditional and the marginal distribution. So you have done, everything has been done in order to be consistent in order to get an actual coupling.
Monsieur, pourrais-vous montrer if we do that, we can do what? By construction.
By construction, P is indeed a coupling between Q and Pn. This means that the first marginal of bold P is Pn, and the second marginal is Q. Okay? And this is true because for the marginal, this is true because when you look at what happens for the n coordinate, this is true. And when you look at the family of conditional distributions, this is true. So this is true globally. And now, about the inequalities that you have in your pocket, we know that for this coupling, the sum square of xn different from yn plus the sum between 1 and n minus 1 of the integral of the p-board square xi different from yi given t dqn of t is less than the relative entropy between Q and Pn over 2, and this is true by the chain rule. So now it remains to relate this sum here with what we want, and what we want is the probability what we would like instead is the sum of the bold probability square that xi is different from yi. But if you look at what happens here, if I remove the square, the integral of the conditional distribution under the distribution Qn is merely expectation of a conditional expectation, that is the probability that xi is different from yi. So if the square was not there, I would reconstruct the probability that xi is different from yi. So you'd see that here, the end of the proof is very easy. You just have to commute the square and the integral. And this has a name. This is Jensen's inequality. So if you use Jensen's inequality, you get that the bold probability square xi different from yi, which is equal to the integral of the bold conditional probability that xi is different from yi given t dqn of t square is less than the integral of the square of the xi different from yi given t dqn of t. And the proof is finished. Okay, so we stop here for today. And I hope to see you on next week in a good shape. So stay safe and see you next week.